Are we? We're live. Excellent. Right, for anyone seeing this as a recording, we're talking about the Jenkins workflow plugin and details of its code. And anyone in the background, can you please mute yourself? Thank you. So I'm going to attempt to screen share here. Let's see if that actually works. No, it does not. No? Okay, that kind of that's that part.
All right. You need to, let's see. How do I do this? What's the like if you rejoin, did that work, or should I show my screen and somehow do we try to make that work, or how do we do that?
Yeah, I guess you can.
For what it's worth, I can see a screen share option showing up.
I can see the option, but when I click on it, nothing happens. So apparently it works for other people. Okay. All right. Well, maybe we just do it via your screen if that works for you.
All right. Well, let's try it. You don't think there's like an easy way to fix that on your side, right?
Not quickly. I think there's some sort of problem with.
Okay. All right. Well, so let's see what we can do.
Outer Chrome.
Is me being your remote hand.
Okay. All right. So just at the top level, what we sometimes refer to as the workflow plugin is really a repository containing a whole suite of plugins. So there's about 10 or so here.
Yeah.
Yeah. So each of these does some different stuff. So sort of at the low level, we have a step API that actually it doesn't depend on anything else in workflow, so it's a pretty lightweight dependency to let people define build steps. And then we have some other modules that build on top of that with the Flow API to define sort of basic things about workflows.
Oh wait, where did it go? Did it got renamed? Maybe.
Okay, is there a setting on your side? I see a ping from Nicholas saying that he cannot join because it says Hangout is full.
Okay. Yes. But he can watch the this show from the event page. So in read-only mode, I guess there's some kind of cap to the number of people who could attend, which is a kind of shame since Nicola being here would have been great. But oh well. Oh.
Looks like they dropped off. So.
Okay, so tell Nicola that the time to join is now. Didn't mean to tell others to.
Take one from the team. Okay. So if you go back to looking at the overview of the code, so Workflow API module gives us some basic fundamental classes relating to workflow, like what a workflow is, what a run of a workflow is, that sort of thing. And probably the most interesting other module is the job module, which defines the actual job type. So this is the top level item similar to a project that you can actually create one of in Jenkins, and then the workflow run is the corresponding build type. Note that these are job and run, not abstract project and abstract build, because they tend to have a different structure than typical projects like freestyle projects or even Matrix or Maven projects, because they can have multiple workspaces, multiple SCMs, things like that, and for other reasons as well. So, and then there's one special plugin that we call Aggregator, and that is doesn't have any source code of its own. It's just a dummy plugin that we use to hold integration tests. And if you HPI:run on this, then it will start up Jenkins with all of the other plugins in this suite loaded. So that's the way that we would normally test out changes and demo things.
And it used to, I guess, the Uber plugin that the user would install, if I remember correctly, right? So
sure. Yeah. Yes. If you want to go to the experimental update center, then you can just check workflow aggregator plugin, and then it will pull in everything else's dependencies for you.
Yeah.
So, do you think it makes sense to sort of start by talking about steps? What I was thinking I would do is go through 3 steps of increasing complexity to sort of see what they're doing and how they're put together and how they run.
Yeah, I think it makes sense to go from step.
Yeah, because I think that's what people are
right.
most interested in, unless you're really trying to make changes to the core. So, so if you can open up step, I guess that's a reasonable place to start. So a step is the definition of a build step in a workflow. So this is marked describable because it's if we had a non-script-based workflow, this is what you would actually have a little configuration form for, etc. And so this just has the it can have any fields that would be the definitions of parameters that you would pass before it's actually run. And it correspondingly has a step descriptor, which is just the class of similar steps. And that doesn't have too much of interest in it. The main thing we'll pay attention to here is just the get function name. So for a workflow script using Groovy, this would be the name of the function that appears in your Groovy script. So you just register a step descriptor, and that has a new instance method that makes a new step given some parameters. Most of the time you don't have to deal with that directly. You just use a abstract step descriptor impl, and that takes care of configuring your step appropriately, so that if you just have a regular Jenkins data-bound constructor with some named parameters and some getters and whatever, if you just extend abstract step descriptor impl, then it will bind everything properly from a Groovy script or something like that. So most steps will extend from this, but you can extend from step descriptor directly if you need to do something special with the syntax. So if we go back to step, then the basic thing that it does is start, and when it starts, it creates a step execution. So the step execution is a representation of the step actually running in a particular workflow. And this gets passed in a step context, which is a pretty important object. It's one of the things it does is it can hold other things like a reference to a logger or various other kinds of useful objects that you might need for various purposes when writing Jenkins code, the sorts of things that would usually be passed in as method parameters. But the step context is also a serializable handle that can be stored in various places, and even after a Jenkins restart, and refers to the particular spot in this particular flow that's running. And so you get a step context every time you run a step, and you can use this to identify yourself. Yeah, and Kosuke just noted that if you want to put questions, I guess, in the chat window or something, I'll see them. So So most of what you do with the step context is either call get to get some information about the context, or you call on success or on failure. And that's how you indicate that your step is done. So in order to support steps running for a long time, which may survive the detached slaves or Jenkins itself crashing and restarting, or being intentionally restarted, or any of this, everything in this API is sort of written in asynchronous style. So instead of you returning immediately with your return value, you call on success with the object that you want to return as the result of your step. And that could be immediately after it starts, or it could be a day later after 3 Jenkins restarts have taken place. So the step execution is the thing that you create that represents your step running in the system. And again, this is serializable because this is going to be persisted in case Jenkins has to restart while your step is still running. So it's holding on to the context. So you can always use the context at any time to get access to various other things.
Right. So the way I think of it, the execution is that comes from you, the plugin developer. The context comes from the scripting engine. And that's how we talk to each other.
Yes. And so you can feel free to define additional serializable fields in your step execution if you need to keep various kinds of state. If you do want to change those values at runtime, then there's a method on step context, I think it is, that you can use to save your current state to make sure that you're persisting those changes. So I think what we can do is go to a simple step. I was thinking the PWD step would probably work to show something very elementary.
Yeah. Bit of jump here because it actually uses all this injection stuff and it doesn't touch the context directly. I don't think you.
Right. Yeah, but I think that's okay in this case because we can just show what some of the superclasses do. So this would just be this is pretty much a bare bones step implementation. I don't think it gets much simpler than this one. So this is just a step which, just like the shell command pwd, it just returns the current working directory that you're running on some slave node, and it just takes that path and returns as the value of the functions that you assign it to something, a script, for example. So it takes no arguments or anything, and so the execution also doesn't need to take any fields that it would save anything in. It uses this step context parameter annotation. This is a way of indicating that it would like to receive something from the context that will be injected, and because we're extending this abstract synchronous step impulse, or step execution, which in turn, no, I guess it's not, doesn't extend anything special. So, well, sorry, actually, because we're extending abstract step descriptor impl for a descriptor, I suppose, is the interesting part. Because we're using this convenience class that looks around for any fields that are marked step context parameter, and if it finds any, then automatically calls context.get with the appropriate class for you, so you don't have to make that call manually.
Right. Well, actually, where is that happening? I think where do we do injection here? I think it's here. No, that's for arguments. So where does the context get injected? I think it's in start. Wait. No, I'm sorry. I think it's here. That's where the injection happens.
Abstract step impulse.
Right. Yeah. There you go. So it creates the juice injector.
And again, these are just convenience subclasses that take care of some of the plumbing for you for the simple cases like this one. And then the more complicated examples that we'll see don't use these convenience implementations.
So these are simple ones. These are not.
Right. So if you go back to the PWD step, so in the execution, this abstract synchronous step execution is just a convenience variant that you can override if you don't need to do anything asynchronously. And in that case, you have a method run which returns your result within the same thread, presumably something quickly, and that immediately calls on success in the context with that value. So you don't have to think about the asynchronous possibility in this case because we don't care for something like PWD step that is never going to run for more than a fraction of a second. So all this does is it gets injected the current working directory. So if you have a file path in your context, that means that you're running on some particular slave or possibly master in some workspace, and the file path is the root directory of that workspace.
Right, so this just is like an indirect way of calling step context or get, and then type is inferred from here to here, so that's what you're getting. Oh, someone used a nice Unicode character. And then that's here, right?
So that's a very, very simple one. It doesn't have any asynchronous character. And it's just a single function call, not even any arguments.
And feel free to interrupt everyone, by the way. I think it's better. It works better that way.
Yes, please do. So next I thought I would look at durable task step, since that's arguably the most important step in the system. It's certainly not the simplest, so this one is going to be more work to follow, but it's also one of the most widely used, so it's important. You can actually open up shell step to see the real step here. This is that all of the implementation is in here.
And I wonder if there's a slightly easier asynchronous implementation, not the one that's...
So there are definitely easier asynchronous implementations. I just wanted to do this one because it's so useful. But you can start with a simpler asynchronous one first if you think that would be useful. Yeah. So what would be
is this like to test code-ish?
You can use watch your step, sure.
Right.
I guess it's a reasonably simple. Well, it's not as simple as it could be, but it's pretty close.
Right. So this captures the essence of asynchrony, right? So the used in workflow function it's still, I guess, use function name for this watch. So you'd use like and then what is happening is you execute asynchronously, right? So the instantiation and all that is just like JC described, and then here so we extend directly from step execution, and then so when the script calls watch method, like invokes it like this, it basically come here in the start, and then so the first thing, so this is basically to wait until the file path exists. So if that already exists, then we declare that the task is already successful, and then return true, meaning it completes successfully. Obviously, more interesting case is the path does not exist just yet, and then so in that case we sort of record the fact that this is pending, and then return false to indicate that the step is now in the asynchronously executed. So what this does is not particularly important because this is really only used for the test code. So at some point, there's periodically watching, testing these things. I think that happens here. And then when the file actually exists, discovered to be existed, then we call on success, right? So this call happens in some random other thread at some point in later, but that signals the fact that this step has actually completed. And at that point, the workflow would look like as if it returns from this method, then resumes execution. So that's the essence of the asynchrony, right? Does that make sense? I hope. And then the extra twist is that, okay, so imagine like the watch method is running, and we want to cancel the execution of this workflow. So the scripting engine would call the stop method in this case. So here, all we are doing is just telling the context that we failed miserably. I guess this isn't quite doing the right thing because we are not really canceling the registration, which is probably what needs to happen here. But again, this is a test code, so it kind of works okay. So that's what it does. All right, back to you.
Sure. So can we open the shell step? So this is So we had a question from Jacob. I hope I answered that. And then we have a question from Nicola. Active watchers are saved in the descriptor config XML. In this case, yes, the next example that I'm going to show, it uses more standardized system.
Yeah, so don't wait. So hold on to Nicola. Let's hold on to that question until the shell step, because this watch step is kind of written for the test and it doesn't do the persistence properly. So it's kind of doing it the pure way.
All right. So shell step. This is what handles the sh command and workflows that just runs a Unix style shell script. So you can see this class is pretty much a placeholder, which is here in case so that we can have a subtype for a Windows batch step and things like that. So if you go to the superclass durable task step, that's where all of the implementation is. The durable task itself is actually defined in a separate plugin. Essentially, it's which is independent of workflow, and that's basically something that can potentially run in the background even if Jenkins has been detached from it. So it's a way of having a forked external process keep on running without having to call home all the time. So Jenkins just periodically checks to see whether it's still running, if it's produced any fresh output that it can display, but otherwise leaves it alone and doesn't try to own it. So the durable task step is how this is wrapped into workflows. So so there's not much of interest in the step itself because all it's doing is defining what the durable task handle is. So in the execution, when we're actually starting this, the start method. So first we find out.
Oh, what happened?
It looks like I got muted. So when we start this step, first of all, we're assuming that we have a workspace. So it's the step context parameter WS. So this only works after we're already running on some slave or something like that. We assume there's some other typical kind of stuff, environment variables, a launcher that lets us launch commands, and a listener to print messages to. So when we start this, this durable task.launch method is the API that we call to actually start the task, and we get back a controller object, which is a small serializable object that sort of keeps track of which process this is, where it's running, and how to get information about it. So how to find out if it's actually finished, or how to find out if it has fresh output, that sort of thing. So we hold on to that controller, we stick it into a field of our step execution. So that means that it's going to automatically be saved if we restart Jenkins, and it will come back in the same state after deserialization. And we also keep track of the name of the slave that we're running this on and the remote workspace path where we were running. So we use those things later on, I suppose. I don't actually remember why we use them. But, and then essentially all you do if you scroll down some, so we have a little helper method to find our workspace again. That's what uses those fields, I guess. And then the meat of it is this check method. So this is called periodically. And all the check method is going to do is it's going to try to attach to our slave, which might have been disconnected and reconnected or something like that. So we see if we can get a connection to our slave, and then we ask the controller for the task to see if there's any new output that comes in. So this write log method is going to copy any output from this forked external process somewhere into our task listener, so into the output for this step. And if it returns true, that means that it found some outputs. We're sort of going to save that fact so that we can keep track of where we were. Because the controller will change. It will keep a pointer into the output that it's saving. And then we also check to see if it's done. So if it's not running, then we just let this check be run again sometime a few seconds later. If it is done, then we just check the exit code and we either call on success or on failure. So you could potentially customize this a bit so that it returns the exit code as an integer to this script or something like that if we wanted to. But right now we just assume that if the script failed for any reason that we want to fail the flow as well. So, and then the checker is a little bit interesting. So it's, they actually plan on changing this a bit, but probably not the fundamental idea here. So basically we're running every few seconds and we're going to check we want to check all of the running shell steps and similar things in the system. And so we use this method set execution apply all, and this lets us do some kind of operation on all of the running executions of a particular type, of our type. And it's written as an asynchronous method because we don't, because you might call this while Jenkins is still booting up or while it's still loading some flows or something like that. So it has to be written so that it runs as soon as it can, and then it gives you a handle to let you listen on what happens to that.
All right, so you should mentally read this as like a for loop that sort of goes through all the execution in the system and then calling this. Right? So like it's almost parallel to be writing like. Yeah, done in asynchronous style.
Right. So that's what makes sure that all of our shell steps get somehow processed every few seconds.
Right. And then, so this is, I think, where we can come back to Nicholas' question. We're in the what step, like, I explicitly kept track of all the ongoing, running what steps, right? Because I needed to see if the files are there. I have to pull them for each one of those. And then, so, later in development, we realized that this is actually a very common pattern. And then so we push that responsibility up to the workflow plugin, and then so that's what this durable task step that's used. So it's asking that, okay, so asking the workflow plugin, all right, so give me all the durable task step execution class that's running, and for each of them, let me call something, and then that's what it does. So back to you.
Sure, I think that's pretty much it for durable task steps, so this would be a good time to ask any questions if you have them about how this works. But if not, we can look at executor step, which I think may be the most complicated step there is. So that should be a fun exercise. So this is also one of the most important steps. In fact, you can't use durable task step without it. This is the step that's labeled node, and essentially what it does is you give it a single parameter label, which is optional. It can just be null. And this tries to lock an executor slot on some node, usually a slave. You can leave the label blank and that'll just look for any executor, or you can specify the label and it will look for a slave matching that label expression. And so the first interesting thing about this, if you go down to the descriptor impl, is that it overrides takes implicit block argument. So every step descriptor can, by default, this would be false, which means that our function just runs by itself. It's just a single call. But if you override this and return true, then you're saying that your step actually takes a block argument, or sometimes called a body or a closure. And it can, depending on what it wants to do, it can run that body once, or it could run it multiple times, or it could decide not to run it, something like that. The one restriction is that we don't allow steps to run their block after the step itself is finished. So it has to be within the dynamic scope of the step. So node on its own just allocates a slave, and then the body is what you actually do on that slave, so running shell steps and other things. So when we start it, we get this executor step execution. So if we jump to that, so basically all it does when it's starting is it schedules something into the queue. So all that happens when the flow script actually gets to the point where you run node such and such, at that point it just schedules something onto the queue and then goes to sleep. And this is done because we don't actually know when we're going to get access to a slave by that name. It may have to wait for other flows or other freestyle projects or all sorts of things. There might not even be a slave by that label yet. You might have to bring one online later, etc. So just like any other queue scheduling, this would be the equivalent of clicking build now on a freestyle project. It just schedules something, and then we wait for one executor slot to open up, and it will start running. So actually, if you look at a typical flow running, as soon as the flow starts running, there's a flyweight task that always is associated with the master. So that will show sort of at the top of the executor widget. And that doesn't consume any resources because it's intended to not be doing any real work. It's just running the logic of the script, which is probably just a few function calls. Whereas the executor step execution represents an actual occupied executor slot. So when you look at the executor widget, once this is started, and once this task has been scheduled, then you'll see the flyweight executor slot on the master running the whole flow, and then you'll also see a separate executor slot on some slave for the body of this node task, node step. And there might be several of these in a single flow. So you might have, a dozen of these things running on the same slave or on different slaves at once, all as part of a single flow run. So we have a question from Robert. He says, QTask dispatcher can have a say in where a step is executed. The QTask dispatcher, yeah. Yeah, so QTask, yeah, so it could. Anything that could affect the queue could affect this.
The kind of contextual information you can get out of just looking at that placeholder. So I don't know how intelligent you can be, but yes.
True, right. So it's not clear what it would base its decision on, but anything that does affect the queue in general could change how this runs. It would change which node it gets scheduled onto.
Right.
So the placeholder task is the representation of the task that we're scheduling. So this is a little bit unusual in Jenkins. Usually a task is actually a project. So a freestyle project, for example, implements task. And so the task is not the individual build, but the definition of the build. But here it's a little bit different. So the placeholder task, one of these is created every time you run the node step. So each one is distinct. And that's what we want, because we don't want the queue trying to collapse several node steps all into one. We want each one to run on its own executor. So that's the placeholder task. And so once this gets actually scheduled onto an executor, then it creates a placeholder executable object.
So usually this is run, but it's not.
Right. So yeah, so normally an executable would be something like a freestyle build, but here they're creating a special queue executable for this purpose. So when we actually have allocated a slave, so we've gotten an executor slot on some slave or possibly master. And at that point, we're just going to record some basic information about where are we running. And then the first time around, we're just sort of getting a handle that we generate to identify ourselves later. Probably don't need to pay too much attention to that here. That's used for several purposes, including killing off stray external processes. And then the next thing that we do is, for convenience, we also pre-allocate workspace on that slave, just like a regular project would do. There's also a separate step called workspace step that you can use to get a distinct workspace on a slave that you've already grabbed if you want to. But since you normally want that as part of grabbing a slave, we do it automatically in here as well. So that's what this workspace list.lease is for. That's trying to get a possibly new workspace on this computer, so that we'll just pick any available workspace. It could add @2, @3, @4, etc. to it if it needs to get a unique one. And then all we do is we call this method context invoke body later. So this is what we do to instruct workflow that, okay, I've done my setup, and now it's time to run my body. So this is just calling your closure. And the workflow engine will run whatever happens in that body. When it's done, it will call unsuccess or unfailed on your callback. It'll let you know whether your body finished and if it returned any value. So in this case, in the normal case, we would get on success called eventually as soon as you're done with that slave, and so in this case, we'll just release our workspace lock, and finish is just going to go and kill off any stray processes and do some bookkeeping cleanup, so that we remove ourselves from various lists, and then we have our context. So this is our own context, the context of the node step, and we're going to call on success with that same return value. So that means that any return value that the last statement inside this block returned, we're also going to return up from the node step as well, just for convenience. And correspondingly, if the body failed and on failure, then we do pretty much the same thing, except we mark ourselves as well.
So the placeholder itself, it's parked in. So this is a state in which it's parked. Okay, so it's looking for this task mode. So it's basically like it's parked until that finish happens, in which case it gets removed from here, and then that exits.
Right. Yeah. So we actually have to go into a spin loop here, or we go to sleep here in this thread, and that's because a Jenkins executor assumes that it's a single run block that we're going through, and so in order to occupy this executor slot, we actually have to have a thread that's just sitting there doing nothing. So it's not exactly ideal, but that's just how executors work. Maybe Kosuke knows some prettier way to do it, but
no, that's how it works.
Okay, that's how it works. So yeah, so it's just going to sit there and wait for some notification that its body completed, and in that case, running tasks will be notified, and it will no longer have this cookie in it, and so we'll drop through to the end of this function and release the executor slot. So that's, and you can, I don't think there's anything else of interest near the bottom of this method. There is, I just very recently added, just double check here. I just recently added something at the top, which is a stop method implementation. So it's going to be up here. So if somebody asks to stop this step, then either it's still waiting in the queue, in which case all we want to do is cancel the pending task. Or it's already running, and if it's already running, then we just essentially ask that we remove something from that list of running tasks, and so that asks the body of the executor to break immediately. And so that should release the executor slot and let us finish. And currently we just do this by marking the whole thing as being failed with an interrupted exception, so we can see that it did not complete normally. So I think, so that's the body of all of this, but we've sort of left out the crucial fun detail in all of this, which is what happens if Jenkins is restarted while all of this is happening. So, so for a normal freestyle project or something, if you restart Jenkins while it's in the middle of a build, then the thread that the executor is in is going to be interrupted, and so that you hope that this is done in a timely, polite fashion, and that it can throw up an interrupted exception and then cause some things to clean up nicely, or it might just have crashed abruptly and not done anything polite. But in any case, that thread that was running the executor is going to die, and since for a regular build, the scope of the build is exactly the scope of that function call that's running on that one thread. It's dead and can't possibly come back. But that's not true for a workflow. So if you are inside a workflow build and it was running a node step and there's stuff that was happening inside of it, then this loop will exit somehow, either politely or just because the VM stops. And so this will obviously die and fall through to the end. Maybe it will have time to go through the finally block, but probably not. That probably needs to be cleaned up a little bit. But at any rate, after it comes back up, then we need to have some way of trying to get back to the state that we were in. And if you go to the invoke body later, it's right at the top of the screen here. The line at the top of the screen is invoke body later. So when we call invoke body later, we pass, in addition to the callback, we pass in a list of other arguments, and these are all things that will be available to the context of steps that are running inside of us. So within our closure, all of this stuff will be available. And so there's a few miscellaneous things, but the interesting thing that we're passing in here is the workspace.
See.
So that's the last argument of this function call. Yeah, and so by passing in the workspace that we've allocated, that ensures that any nested steps know what slave they're running on and what directory in that slave they should use as a workspace. And what makes this magic is that we have something called a workspace lease pickle. Workspace list lease pickle. So this is, oh sorry, this is not part of the context, I guess, but this is part of the state that we're storing inside the executor step execution. Is that we have some field where we're storing a workspace list.lease object. And so some things in Jenkins APIs are serializable in an obvious way. They're just some kind of data, and we want to serialize them and deserialize the same fields. But then there are other things that we might want to serialize as part of the running state of a flow that can't just be stored directly. We really want to store a handle to them. The workspace list.lease is one of those things. It's not, the actual class lease is not serializable. It was never intended to be. It's just something that's supposed to be used within one Jenkins session. So when we save and resume this flow, what we want to do is record the fact that we had locked a particular workspace on a particular slave. And if and when we come back up, we want to find that slave again, and we want to relock that exact same workspace so that we can have all of our stuff run in the same environment that was running on when we were last, during the previous session. So at the bottom of this class is the factory for it. So this is the actual extension. So you can register so-called pickle factories that allow you to store a particular kind of object in a different way.
So the way I think of this is, the workflow, executing workflow has this large graph of, a graph of objects that sort of defers to various things. Some of these things are, say, like a rather innocent things, like if you have a for loop and the loop variable is I, maybe at the point of that suspension I might be 3. But some other objects are a bit more, really more stateful, like this workspace. So when we are executing this, when the workflow suspend in the middle somewhere here, then there's this implicit variable that you can get through the context that point to the current workspace, right? That's a file pass object. So that file path is a part of this object graph. So when we persist the state of the running workflow, that object graph would contain the file path. So the way we hide this, like how we relock the workspace and so on, is by sort of kind of like an interception layer at the point of persistence. We can't just persist the file path because it contains a channel object. So we replace that with something else called pickle in the actual storage format, and then when it read back, we would try to read that like a storage format into the real live file path, and that's where all the relocking happens. So so that's the whole idea of like a pickle and the pickle factories and so on. And then in this case, we are using that to resurrect the workspace. So the workspace meaning the file path, right? So any file path variables that the workflow might point to, we'd be able to use this code to get the same file path back.
Well, there's actually a file path pickle, which is slightly.
All right. So clearly, I said. So it sounds like what I said was a lot.
It's very similar. So the file path pickle is.
So this is getting
very
a
similar
leaf,
code.
not
This is for a workspace list
yeah.
leaves.
Sorry.
But the code is very similar. A file path pickle is just for a file path that you don't have any particular claim to. Whereas a workspace list lease pickle is for a workspace that you've actually locked and intend to get back for yourself.
Right. Sorry. So I got those two things confused.
Yeah. But they both keep the same two serializable fields: the name of the slave and the path on that slave. And they do something pretty similar when they're storing and when they're coming back. So when we store it in this constructor, we're just recording the name of the computer and the path on that workspace that we've locked.
Do you want to look at the pickle and pickle factory?
Sure. So pickle factory is pretty uninteresting. It's just a factory for pickles. You give it a live object and it replaces it with a pickle. And then a pickle is just some sort of opaque object that you can rehydrate is not exactly the right metaphor for talking about pickles. It would be more like debrining or something. Something to get back a fresh object. And this is a listenable future because we may be blocking for a while, so we can't guarantee that we'll be able to restore it right away. It may take a few minutes or something, depending on what it was pickling. So if you look in the workspace list lease pickle, so the constructor just saves a serializable field, so those get deserialized in the normal way. And then in rehydrate, we're going to try from time to time to see if that slave has been reconnected and if we can get a live connection to it, and if we can actually relock that workspace for ourselves. And so Robert is asking, so file path with the workspace as a parent will be deserialized correctly after the workspace has been relocked. Yeah, so file path, rehydration from file path is simple because it's not trying to lock anything. It's just going to return, as soon as the slave is online, it's going to return the file path. Workspace list lease pickle is a bit trickier because it has to lock the workspace as well. So this acquire a particular path, this is supposed to be acquiring that particular path, not locking, not looking for some other random clone of the workspace, because we can't use a fresh workspace. We really need to have the same one back. So, and then there's one more pickle that we're using here, which is executor pickle. I think. What's it called? Executor pickle?
Mm-hmm.
I think so. Yeah, so because our executor step execution, I guess somewhere it was storing an executor. It must have been in one of its fields or something like that. So because we pickled that executor, or because we were storing that executor, it gets saved as a pickle, and the pickle in this case is a representation of the task that the queue scheduled onto this executor. And so the idea is that if we come back after a restart, then the way we get our executor back is that we just try to reschedule the same task that we had running on it before. So we're going to schedule the task, and then you keep on waiting to see, and actually remember what the implementation is here, but essentially you're trying to wait to see if some executor slot on a live slave is now running your task, and as soon as it is, then we return that as the value of our pickle.
Yeah, we need a better way to get to the executor.
Yeah, I mean, there's probably some
Maybe like
slight variants we could do in Jenkins core to
yeah.
get access to that more easily. But right now, it's just sort of scanning all of the executors to see if it's running yet.
Yeah.
But essentially, as soon as the queue schedules it, we want to return that running item. So put together, it means that after the executor step execution was started in some previous Jenkins session, if it actually got scheduled onto a slave, then those objects get stored into the step execution state. They get saved as these pickles, which are just sort of little lightweight objects with just the elementary data. And after we come back from a restart and the workflow engine is trying to restore our flow so that it can be run again, then it looks for any pickles that were part of the flow stored state and asks to restore all of those pickles. And once they're all resurrected somehow into live objects, then it begins running the program again. And so by that point, that means that we'll have scheduled this task, rescheduled this task onto the queue, and it will have also been scheduled actually onto that same slave, and it will have locked the same workspace on that same slave. And so then we're ready to go. We can resume execution at exactly where we left off. So, and if we were in the middle of a durable task step, then that shell command or whatever it was may still be running on that same slave, and we can go right back to pulling in console output or something from that same shell step. So this was the tricky part. This is sort of the magic of resurrecting everything after deserialization. So I hope there are some questions after all that. Let's see if nothing coming in.
I hope
we're at an hour. I'm not sure if we actually scheduled any more time than that, or.
Well, I think we should keep going. It's just a recording, and then people dropping off is okay. And, yeah.
All right. Let's see. Kosuke, do you want to give an overview of the Groovy CPS engine, maybe, or?
Right. So actually, I think we need to start with flow definition and so on. So it's like abstraction. So far, okay. So the step. So far, we looked at the step, which is like the things that implemented by plugins, the workflow equivalent of build step.
Wait, hold on. We have a couple of questions. Maybe we should deal with those before we move on.
All right. So what sort of steps do we expect for the people to contribute? What are these? So, well, so I guess in general, like anything that people have written build step for, I think those are good here. In fact, I guess we kind of skip the whole area of intro of build step, but like handing off the external tools or any lengthy process that you want to encapsulate as a synchronous execution. So let's say like a deployment to somewhere, starting a new server, launching a new EC2 instance. I think there's all sorts of things that can be useful to be driven from workflow. So I guess those are the ones that we think of.
Right. So I should actually say something about the interoperability. So for anything for which you already have a builder or a publisher, which doesn't need to run for a long time, so it's either really quick or everything that it does really involves live communication with the master to stream information back or something like that, which is a lot of build steps. Any of these things you can now run from a workflow as long as you implement this new interface in Core called Simple Build Step. So Simple Build Step is just a generic definition of something that can run without any very particular context. So it's given a workspace, unlike a regular build step, which would typically assume that the workspace was part of a particular project. So it's given the workspace and then the usual stuff, a launcher and a listener. And perform method, it's expected to run synchronously and either work or throw an I/O exception. So any kind of really straightforward thing like that, all you have to do is implement this new interface, and then there's a special meta step in workflow, which I call core step for now, that just allows you to run that build step from your workflow. So that lets you interoperate with a bunch of things without having any new API dependency, essentially. And for long-running steps, which are basically running some sort of external process and then essentially just waiting for it to exit and collecting output. Obviously, you can use the existing shell step, but if you want it to be easier to launch, so if you want to integrate with a particular tool definition or something like that, then right now the only way to do that is by integrating with the durable task plugin. But I hope to add a way to sort of do this more automatically for the common cases. I haven't yet drawn up this API, but I think there can be something where you just sort of implement a simple interface and describe how you want to launch the process, and then you could sit back and it would become usable from a workflow and survive restarts and all of that. But then if you want to do anything more subtle, so certainly if you have anything that you want to take a closure, a block, or if you just have stuff that's sort of inherently asynchronous or that you need specialized behavior for of any kind, then you can just have a dependency on the step API, and that's all you need to implement a lot of steps. And it's a pretty lightweight dependency. So. And then we had a question from Robert about dynamically allocated slaves. So this is something that I actually planned on playing with in the very near future. So obviously, if you're running some sort of long-running flow on a remote slave, like something on EC2, then there's going to have to be some way of informing Jenkins that you want to reconnect to that same exact machine and not shut it down if Jenkins does crash and comes back up, so that you can get back to that same workspace and resume your build from there. So I need to do some work on that soon. It may require some kinds of hooks in Jenkins core, either that or some cooperation with the cloud plugin. So I need to figure out what that is. But that would be the idea. That in the case of a workflow run, and well, specifically the executor step, that should sort of hold the slave open and alive, and not let it be released to the pool of the cloud just because the slave channel happens to be closed.
All right. So yes, so now so far it's all about steps, which means it's like a little function that hooks into the workflow. So now sort of look at the other side of the contract, the side that implements step context, the side that provides the entire, essentially, the scripting engine. So I think that starts from actually flow definition. So this is the abstraction of the scripting engine that encapsulates. So you imagine like the subtypes that would actually capture the script to be run. The subtype, the implementation of that subtype would be specific to a certain implementation language, and so on. So we call that the CPS. The one that we have today that's based on Groovy is called CPS. And then, so whenever we start executing, actually, in preparation for start executing, we call create. And then, so that returns essentially running instance of a scripting engine. So you might even almost think of it as a kind of like a virtual machine of its own, like a little world onto itself that's running stuff. And then, so first you start execution by calling start, and then obviously asynchronously behind the scene, this would start running script by calling all sorts of steps and so on. And then as this execution happens, we leave the record behind. So that there's a whole so those records are called flow node. And then so you can mentally think of flow node as, I guess, like as like a call stack. Well, what is this? It's like a graph of so every time you call a new step, you create a new node. Every time you call into a new function, you leave that trace. So it's like a step-by-step record of how the workflow script has executed.
It's worth mentioning that you can actually see these things if you run a workflow and you go to the index page of the flow run. You'll no. So Tom asks, is it a tree structure? No, it's actually a directed acyclic graph structure. So it starts with a single source node, which is the flow start node, and finally winds up closing with a flow end node.
Let's come back to that a little later. Let's for now, let's leave that aside. I guess you'll do this. Yes. So then anyway, for the timing, suffice to say that that's just about like creating the record of what it happens, with enough information that allows us to do visualization and some analysis of the execution. Right, so here, the heads are just basically saying what's currently executing at the very tip of it. So, if the workflow script happens to be running a Maven test that takes 1 hour, then this is probably going to return a node that indicates that corresponds to that, like a shell step, right? And then this is also another view of what's going on currently, but this one returns step execution, which we just looked at. So this is point to the stuff that's already running. So again, in the example of Maven test running for 1 hour, this should be an instance of which one? Durable task step execution. So again, it's just point to what it's doing so that we can cancel it, we can inspect, we can show in the UI what it's doing, that sort of stuff. And then there's, I think, it's like a method like canceling in the middle. So again, this is kind of the abstraction around what the scripting engine is doing and what you can do with it. Okay. So what does CPS flow execution actually do? Is that useful? Yeah, I guess we should talk about that a little bit. So actually, owner. There's one thing that I missed to talk about, which is the owner. So why did we need this?
So the owner is basically a representation of the workflow run, which is to say the build.
Right. So like it's kind of some kind of domain objects that surround the context of the workflow execution. And then so it provides, what does it provide? Yeah, it provides basically, I think I think the primary purpose of this is to assist the getting back to the flow execution itself, or like providing a stable pointer to it so that it can be persisted. Yeah, I think that's right. I think that this is
something that can be, that's serializable, so it can be saved as a field in any kind of ongoing execution for various purposes.
Right. So okay. So how does this CPS flow actual implementation look like? So CPS flow definition is their implementation for flow definition. So in Groovy CPS, the script is just a string that looks like a Groovy script for now anyway. And then so once we start executing, this is what we get. So CPS transformation sort of is like you can think of it as creating interpreter. It's essentially a brand new interpreter of Groovy. So what we do here is there's a class that captures this the sort of essentially running state of the program. So there's a part, the CPS flow execution class, all kinds of methods in here can be called from various UI threads and so on. But when it comes to actually execute the script, you have to be a little bit more careful. So there's a pretty significant separation between those two executions. So the stuff that belongs to the running state of the program and anything that affects its state, that sort of is executed from a single thread, a single executor. So that's I think that's in somewhere here. Somewhere here. CPS flow execution. I thought right. So that's here. This runner. So that's this is the one that ensures that there are state mutation on the running workflow Groovy VM is done from a single thread. And then in the CPS execution, every thread, every virtual thread, and every call stack is kind of treated explicitly. So this can be primarily thought of as the collection of thread, which is each executing some stuff, right? So so this is the actual meat of the stuff to be remaining program to be executed, yeah. So I think that's the general state of it. So when it comes to time. So the way you think of it is that most of the time, like the CPS thread group, so that is the running CPS virtual machine, is frozen. It's not doing anything. And then every once in a while, it do run some things. It do run programs synchronously up to the point of the next thing that happens, next thing that needs to be run asynchronously. So the script might run a few lines until it hits this shell step execution, in which point it forks off a new shell, and then it pauses again. And then that pause state would remain for say 10 minutes or 15 minutes, however long it is. And then when it's done, it runs a few more lines until it hits the next thing. So that's how it goes. So most of the time, so this thread is just really remembering what to do, and then so when it comes time to resume execution, so we get the result. The outcome is just a pair of the result, normal result and abnormal result. So to resume the execution of the CPS thread, you need some result. of the previously pause, the result that caused the pause, and then so we remember that value, and then we start re-executing, and then so by scheduling the run into this single thread, and then when the actual execution is happening here. So we look around all the threads, see if anyone is runnable. If so, we make a little bit of progress until it pauses again. And then, depending on what happens, we might fail. That thread might fail, or that thread might, be put into the waiting queue, or that state. Or if everything is done, I guess the entire program would finish. So that's what it does. So while Groovy script is executing synchronously, it really runs like a normal program, right? So all this when the script calls, let's say when the script calls something like node. And then, so how does this node invocation translate into a function call? So that happens in a class called DSL. So this is, again, I deleted that, but like that, what is really happening is there's this like implicit of the delegate. So that's what's really going on. And then so this delegate variable that refers to the instance of this DSL class. Come to think of it, it's really put a name now, but so it comes here, the invoke method. Right, so in that example of like a calling node, the name is node, and then the arguments are, I guess, the list of objects. Right? We try to look up. Okay, so if someone wants to call the function named node, who is it? So we look up why do we create a tree map? We asked around all the step descriptors, like who is node, and someone. So we're gonna call that guy. Call that guy here. Where is it? Okay, so we create the context and we call that guy here. Depending on whether it executed synchronously. If it has completed synchronously, we are good. So we have a result. So we move on. And then this method would actually return synchronously. So the Groovy is happy and they get the result back and it keeps on going. But when it starts, when the step tells us that we want to execute asynchronously, then we call this magic function called continuable suspend. And then the signal to the Groovy CPS interpreter that we're going to pause the execution. So this is actually like the magic instruction is really just throwing an exception of a special type that gets by a CPS engine. So the exception that's thrown here would actually come into the CPS thread run. And then, so it comes back from here. So this method would actually return normally into outcome, but that outcome captured the thread task that was thrown. So here in DSL, so this is the thread task implementation gets called here. So now we get to execute some stuff outside, like after pausing. So at this point, like a Groovy interpreter is frozen, so we get to do some additional processing here. In case of asynchronous execution, what do we do? What do we do here? I don't think it's here. So yeah, if the body invocation is requested, we're gonna start fork off another thread to run that. Otherwise, I guess we would just pause, remember where the pause is happening, and basically keep on suspending. And then the Daniel Beck asks, how are we going to handle method name collisions? So right now, as you can see, there's no provision for that. So if two steps claim to declare the same function name, then too bad. So I don't know. Maybe we can do something better down the road, but that it is what it is. So let's see. So what else would be noteworthy in CPS?
So maybe we should go back and talk about the flow nodes, unless you want to say something else about CPS.
Yeah, I think in the interest of time, I think that's probably enough. There's a lot more details to the actual CPS, but I don't think that's particularly relevant here. All right, so I guess back to you for flow node, or should I do that?
Sure. So a flow node is just a node in a graph which represents a trace of how the execution of the flow actually proceeded. So this is not statically computed based on the script or anything like that. This is just a graph that's constructed on the fly as you actually run stuff. So initially you just have a flow start node, which is sort of the entry node, and you start adding new heads to this graph, so new nodes that aren't the parent of any other nodes, as you run stuff. And a lot of these are block structured, so they contain other nodes. And so these would be called block start nodes or block end nodes. And so essentially this just records the fact that a bunch of things happened inside some kind of logical block, which in the case of Groovy CPS engine might actually have been a Groovy block that would be common. But it could also be a block scope step with a closure, or a while loop or anything like that would all create some sort of block scope node. And so the flow graph actually puts together a trace of the execution of everything according to how the program really ran. And the most interesting things in it are going to be atom nodes. These are an atom node is just a node that represents one single thing, not a block, and they'll typically have a step attached to it. So that will be what happens when you actually run a particular step. So is there something called a step node? What are the subclasses of atom node? Step atom node.
Atom node.
Right. So that just records a particular step ran at a particular point. And so to Tom's question, it would look more or less like a tree if it weren't for the fact that there is a parallel step which can run multiple threads, or in the future we may add other kinds of, a fork spawn kind of step or something like that that allows you to have multiple threads of the flow running concurrently. And so each of these will have their own kind of distinct branch of the overall graph. And then you'd have a join node at the end when all of the threads complete or are killed, whatever the case may be. Then there's a final node that has a parent corresponding to all of those branches that pulls them together. And Tom asks if this is part of restarting a failed build. No, this doesn't really have anything to do with. So the flow graph is only a record of what happens. It can't be used to control anything. So this is mainly used for display purposes, and so that the overall build log can know what was happening in what thread and record logs for it appropriately and things like that. So restarting a build is a feature in another plugin that has to sort of cooperate with the Groovy engine. But so essentially, when you have this this graph of flow nodes, and you can see everything that happened. And each of these flow nodes can have some actions attached to it. So these are just regular Jenkins actions that you can define custom actions if you want to record some kind of special information about it. So the most common one is label action, which just assigns a display label to this particular node so that you can give it a pretty appearance and some kind of execution graph. Log action keeps track of steps that sent anything to the logger. So if you ask your context for a task listener, then you get back basically a print stream that you can send textual output to. You can hyperlink it as well. If you do that, then a log action gets attached to the node recording your step. And that has its own individual console log for each step. So you can look at the console for a single step, and then the flow run will automatically merge together any output from any running steps and create a consolidated build log as well. But it can be useful to look at the individual logs, especially if you have parallel branches. You want to see what happened in each branch separately. So. And then there are some other particular steps can define their own actions. So I think the input step that prompts you for human input, I think that adds an action to the node to record the fact that it's waiting for input, I believe.
Actually, it doesn't add that to flow node, not yet.
Oh, it doesn't.
It should do that, but it's just adding it to run.
Oh, right. Okay. So right now it's adding it to the run, but
yeah.
But if you had some other reason to record some sort of information that might be useful to visualizations of the running flow or something like that, then you would do that as an action you can attach. And we'll probably have to expand that and add some more standard actions and so on in the future. So right now the important ones are the label action and the log action. And do you want to pop open? We should open up workflow job and workflow run just so people can see those, since we've just sort of alluded to them. So the workflow job is the actual top-level project type that defines a workflow, and so its most important field here is the flow definition that defines what the flow is. And other than that, it behaves pretty similarly to any other kind of job. You can schedule it. It has a list of builds. It can take job properties such as a list of parameters, all of that stuff. So it's roughly comparable to a freestyle project or something like that as far as this goes.
There's lots of overriding methods.
Yeah, just lots of boilerplate to get everything to work. So it also implements tasks. So when it's considered as a task, this is the flyweight task attached to master. Because when it's running, it's not expected to be consuming real resources. And then the workflow run is the representation of a single build of the workflow. And so again, a lot of it's Jenkins boilerplate for extending run, but the interesting stuff is in the start method or run method, I guess. Run method. Yep. So that's what initially creates the flow execution and registers in various ways and starts listening to the progress of the flow execution. And then it calls this wait for completion, essentially just sits there and sits again. So again, this is another busy loop. This is what's occupying the one-off executor slot on the master, is this busy loop wait for completion. that's sitting here waiting to see if the workflow finishes. And in the meantime, all it does is copy over the log messages from any running tasks. So that pokes around into the flow graph to see if it has some new heads that are in there and to see if they have a log action with some console output. And if they do, then it tries to copy that over into the main build log so that you get a consolidated build view. And so that's most of workflow run. Then a little bit lower down in the class, there's the implementation of flow execution owner. So this is the persistent handle to the build. It's down further. Yep. So this just records what build it was based on the name of the job and the build number or build it. And lets you get back to it. And then the finish method, when the workflow finishes, down at the bottom of this class, keep on scrolling down. Yeah. So it keeps track of any new flow nodes that come in, so anything that's happening, and then if it sees that it's gotten a final flow end node, then it shuts everything down and closes off the logs and sort of cleans up in the usual way. So note that this finish method can be called in a different Jenkins session from when run was first called. And so again, we have to do something special to deal with Jenkins being restarted in the middle. And that special thing is in the onload method here, which I think is partway up. Yep. So in the onload method, if we've restarted Jenkins and we're reloading this flow run, but it's not finished yet, so the flow is still running, then we just reopen the log file and just start copying logs again. And the only sort of tricky thing we have to do is we schedule an after restart task, which again is something that just sits there in the one-off executor slot on master and sleeps waiting for the flow to end, so that you have a representation of the flow running something you can click on to get progress or cancel. So Tom's asking if you can talk a little about stages. Okay, sure. Yeah, that's a good thing to open up. Do you want to? That's actually a pretty interesting step definition. Yeah, so it relates to the flow graph. The quick answer is that it doesn't. So if you run a stage step, it adds a label action to the flow graph indicating that you're in some stage, but really that's about the extent of it. So it doesn't do anything very exciting to the flow graph, although it adds that hook that you could use for visualization.
Well, that's not, well, so it does leave enough trace. So, when, for example, like Tom would probably want to know when the execution would have moved on to the next stage, right? So those things are actually discoverable. Time that step gets called, it leaves this second corresponding step admin node, and from there you can see what kind of step type it was. So from there you could match it. Now I think what we don't do is we want to remember what stage it went into. So that information needs to be attached as a action into.
Right now it just attaches a label action.
Right. So that probably part needs improvements, but
Right. Yeah. So it could. This is an example of a step that could profitably define its own custom action type and attach it to its node so that you have some information about it. Right now, it doesn't bother. It just adds a label action. And yes, it kind of slices across it. Yes, it does sort of slice across the flow graph, and there's only one stage active at a time, even if you're running parallel branches. So it's not. So the stage is not a property of the current thread. It's really of the whole flow build is in one stage or another stage. And the stage step is basically, it's just something that allows you to gate access to successive stages. So if you set a concurrency parameter to some number, then the stage step will make sure that only one build of this workflow job is running in that stage at a time, or only up to that concurrency number of builds at a time. Usually it's set to 1. And so it has a kind of a fun implementation in stage step execution. If you open that up, it's a nice example of an asynchronous step.
So what happens if someone there's no way someone can, I know you kind of looped over this, but let's go back over again. You can't actually have things running in parallel and two flows running in parallel and somebody in those flows starting two separate stages. I don't think you can, but how does that actually work in reality? How do you stop that happening? Or does that make sense?
So if two builds of the flow try to enter a stage with concurrency set to 1 at once, is that what you're asking?
I guess so. Yeah, I'm not really sure. I'm just kind of wondering how the stages kind of line up. How do they line up as such? So
the first build that makes it in is just going to start running. So if you really need to see stage step execution. So, and the enter method in particular is where everything happens. Yeah, so in the enter method, we sort of look up some metadata about whether there's already some other build in the stage or what's happening. And if no one is already in the stage, or if there's fewer than the concurrency limit others in the stage right now, then we just immediately go ahead and enter it. And so we call, at some point down here, we call context on success null here.
Yeah.
So somewhere further down in this method, we blah blah blah. Yeah, it says proceeding, and it just carries on and continues with the rest of the flow. But if somebody was already in the stage, if there's already concurrency other builds in the stage, then it just says waiting for build. So it tells you which builds it's waiting to exit before it can enter. It just prints that, and then it goes to sleep. So since it doesn't call context on success or on failure, it just effectively sleeps at that point. But then in other cases, we can unblock a waiting flow. So if we leave a flow, if we leave a stage, then we're unblocking any other flow runs that we're trying to enter that stage, and so it's going to print that message to that other flow run's log, and then get that other flow run to continue.
So how does that work? So when do we leave?
That's pretty much everything is in the enter method.
So you don't call exit from there. All right.
No, exit is only used if a flow completes. Then that effectively means that we're exiting whatever stage it was in. But most of the things happen inside enter. So if
okay, so I guess this is actually the part of the processing that's leading. Is that right?
So the current build is trying to enter this stage, and we say, okay, if waiting context is not null, then somebody has to wait, and so we're trying to figure out who should be waiting and who should be proceeding.
So this is when we are. I'm not sure if I follow this correct.
So maybe if I can reword my question, because I don't think I really asked it properly. If you have in a single run, if you've got parallel steps,
Okay.
and can you mark a stage in both of those parallel set of steps, or
You could, but it would be pretty silly because it doesn't pay any attention to what thread it's called from. It only matters the whole flow run as a whole is in one stage at a time. It doesn't matter what thread the stage step was called from. So typically it wouldn't make sense to call this step from inside parallel step. I mean, you could.
Yeah, that's what I was thinking. If someone did it, what would be the outcome?
Nothing special would happen. It would just be, whichever. It would just be like running the same step at top level outside of the parallel step. So.
Okay.
Yeah, so this is essentially sequential, and it sort of has to be that way because by entering a stage, you're implicitly exiting the previous stage, and so we're sort of leaving that walk. You could definitely define. So there's nothing in this step that does anything magic. So this is just using pretty standard step API. So you could define another kind of step that has other kinds of blocking logic, but that does something interesting in parallel branches if you wanted to. This one doesn't. This one is just designed to only work with a linear sequence of locks, and each time you acquire a lock for the next stage, you release the lock on the previous stage.
Okay.
As you move through. But yeah, other kinds of lock implementations you could define as steps without, just in whatever plugin you liked. There's nothing weird you have to do for that. And it's a little bit interesting here that we can actually print something to the log of another flow run than the one that triggered the center method. So we find some other stage. So we find some other flow build, and we want to unblock that one, but block ourselves, or continue with something else ourselves. But we can just call. So 3 lines down from where the curate is here, 4 lines down.
Why do we loop here?
So
okay, so it's what is it? I thought the way I kind of anticipated the code to read. Okay, we know what stage we were in, so we're gonna look at that to see that stage that we are about to leave, and then we're gonna try to figure out where to see if anyone is blocked on that, and then so that's this part, right? So that's the part where we say, okay, so who's waiting in the state that we just left, and then allow that to proceed. So why is that a loop? I guess because we don't remember.
Well, I don't know, but it probably doesn't matter for purposes here. I mean, as long as you get the idea that it's just keeping track of which set of builds is in each stage, and then letting particular builds either proceed or pause, waiting for other ones. So that's basically all this method is doing. And then there's one other special thing that this can do, which is called the cancel method. So if we know that there's a newer build that's also waiting for the same stage, then there's no purpose in us ever proceeding because we never want to continue. We want to let that newer build get into the stage instead of us. And so in that case, we can call a cancel method, and that just aborts the current build. So it just stops it right here. So this would, with chained freestyle projects, this would be the equivalent of an upstream build triggering a downstream build, but another upstream build later on comes and re-triggers it, and so this doesn't wind up actually being upstream of anything. It sort of gets overridden by something else.
Like this guy and this guy.
Yep.
All right. Okay. So I think we did cover the key parts. Anything else, or did we leave everyone really confused?
Confused at a higher level. I think I got good chunks of it, but a lot of it is stuff you just have to kind of step through the code and see what's happening, what the world around you is like at particular points in the code. You can't kind of having someone walk you through. You don't really get it the same way. I don't think. Well, I don't know.
Yeah.
The hardest part, I think, is keeping track of the things that are happening asynchronously. So that makes it harder to grasp than some other things of the same size would be.
All right.
Brilliant. Thanks, lads.
Thanks.
Thank you. And I guess this should be available somewhere on YouTube, I guess.
Yes. I'll post that when it becomes available.
All right.
Okay.
Thank you, everyone, for joining, and everyone who's listening in.
Bye.